Greetings and welcome back to a new video. We continue with our Middlebrook's Extra Element Theorem and we apply to another circuit. This time we will use the second order RC circuit. We will see how we can use this theorem to determine the transfer function for this example. So let's see what we have. We have the following objective. We would like to use the Extra Element Theorem, EET for short, to determine the transfer function A given by the output voltage over the input voltage, so V over Vi in Laplace domain. You see here the circuit. We have in total 3 resistors, R1 up to R3 and C1, C2 and C3. This looks like we have, for example, 3 capacitors, so you might say this is a third order system or third order circuit, but it's actually a second order since the C1 is actually parallel to this voltage source at the input. But we'll see that clearly why this is a second order and not a third order system. So the formula we have discussed also in the previous examples is this. This is actually the formula we need to use in this Extra Element Theorem. We have here a couple of parameters. The first one is what we say the gain or the transfer where the element, what we call the extra element, is open or the impedance is infinite. We have what we call the Nulling impedance and we have also the driving point impedance. The Z is here the impedance of our extra element we have here chosen. So we can choose actually any component here to make it our extra element. In this case we will designate the capacitor C2, this one, as our extra element, but it doesn't really matter. You can also take the C3 or R3 or whatever to complete this assignment. In this case, since we have chosen for C2, that means the impedance is then 1 over SC2, which is then in Laplace domain. So the Z here will be then replaced by this expression. Okay, we start with the calculations. First step is we remove the C2, which is our extra element we have chosen, and we will calculate the voltage gain, and that gain is actually this part of this expression. So we have our circuit back and the C2 is opened here. You see here again the rest of the parameters are in the circuit, so we will now calculate the voltage gain. So in this case we see here the voltage Vi is parallel to the R1 and also C1, so that will not have an effect. You see here now actually a series combination of R2 and R3 and also C3. So we will have a voltage divider rule. So the reactance of this C3, which is 1 over SC3, as we have it also for the C2, divided by the complete impedance seen by the input voltage source, which is then R2, R3 and the series combination of this C3 reactance. We can also multiply the numerator and denominator by SC3, so we get actually this nice expression. And this is now what we have here in our expression, which is the A for the condition Z is infinite. Okay, that's step 1. Step 2 is going to the disabling of our input source. In this case we have an input voltage source, that means it will be a short. And we will then determine what we call the driving point impedance ZT, which is again between the nodes of the C2 here. So this is the circuit. So the input is shorted, so that is actually gone. And we will look at these 2 nodes in here and we call this ZD. What do we see? Well, this is now shorted. That means this is going to ground. That means this complete part is now grounded. That means actually that you see here to the left, you see the R2. But you also see here the right side, you see R3 in series with the capacitor C3. That means actually the following. So the R2 is actually then parallel to the series combination of R3 and C3. And that's actually what you see here. So the R3 is in series with the capacitor C3, which is then the reactance of this capacitor, in parallel with this R2, which is then actually shown here. Now if we now work it out here, this part, the first part here, the R3 plus 1 over the SC3, that is then given by this expression, which is then using this and make it a 1 fraction. And then we can use again the formula for the parallel components, and then you get actually this. So that you multiply the R2 and this expression, which you see here, divided by the summation, which you actually see here. We can continue by simplifying this expression. So you can say multiply the numerator by SC3 and also the denominator. And then you get actually R2 times this one in the parentheses, divided by SC3 times R2 plus this SC3R3 plus 1. That's actually what you see here. Okay, we can now further simplify this expression of ZD. You see here the S times C3, also here S times C3. We also see here R2 and R3, so we can take these two resistors in the parentheses and then make actually this expression. Okay, now we go to the step 3, which is then the null, the output node, which is actually nulling this node, setting to equal to 0 volts. That's not grounding necessarily, so in this case that's the important condition. And that will allow us to determine the nulling impedance Zn, which is this parameter here. Again, we look then between the nodes of our extra element, which is then between the nodes of C2. So that's the circuit. You see again the input voltage is back in the picture and also the other components are there. Only the C2 is again removed, so we will look again between these two nodes, and that's called what we say Zn. So we see here the new condition, VO, which is our output voltage, is then here zeroed or nulled. What do we see here? Well, we can determine that in a more convenient way by applying here a test source between these two nodes. In this case, I call this a test current source, IT, and the associated test voltage source, VT. The ratio VT over IT will be R Zn. That is using Ohm's law. But let's go here step by step. Since this voltage here at this node is 0, that means the current through this capacitor C3 will be also 0, because this is ground and this is 0, so that means minus 0 volts minus 0 volts. So you have actually 0 volts across the capacitor divided by this reactance will be 0 amps. Since this branch is open, that means the current through the resistor R3 is also 0, and its voltage across this R3 will be also 0 volts using Ohm's law again. So current times the resistor. Now, since this is 0 volts and this is also 0 volts across the resistor R3, that means this node is also 0. And since this node is grounded, that means the voltage across this test current source is also 0, meaning VT is 0 volts. The current in the left branch, which is of course here active, that is not 0. So you divide actually here, divide by non-zero value. But you have a 0 in the numerator, that means Zn will be then 0. That is the conclusion for this step. Okay, we take down the step 1, step 2 and step 3 results here for our formula, and now we will substitute these in the formula for the extra element theorem in this case. In this case we will also use this Z, which is then here, but we will use it as 1 over Z, which is then S times C2. So you see actually this in this detailed form. 1 over that complete expression, which is then in front of this one, and now you see 1 plus the SC2, which is our 1 over Z, and then times the Zn, which is this part, and again for same thing but then using the ZD. Now this is 0, and this is then of course this big expression. Now we can substitute that. You see here again the 0 and now also the ZD. Now we can simplify this further, so we get rid of this one. So I continue to the next step. What I do is I will do the following. I will multiply the numerator here and the denominator by this term, which is then SC3 times the R2 plus R3 in parentheses plus 1. Why I do that is I want to get rid of this fraction here. So I get this times that one, which is then of course 1 plus that. And 1 times that actually. And also here I get the exact same. And I get here S times C2 times this complete expression here, so I get actually this one. I recognize the following. This expression is the exact same as this expression, so I can cancel it out. So that's actually the next step. And this is now, of course, a more simple expression. You see here a second order term already appearing. That's because of these working out of these parentheses, so S squared and then also times the 4 components here. I also have S times C2 times R2 times 1, which is then of course this. And I also have this one. So I see here a second order term, first order terms, and a constant 1. So I can bring it now in a form which is convenient. So higher order, first order, and then constant. So second order, first order, constant. And this is now the expression actually we are looking for. That's the transfer function in the Laplace domain for this circuit. We can give it here a more detailed form, also the j omega domain, which is then setting to S is equal to j omega, which is the steady state analysis. That will be then 1 minus this omega squared times the product of these components again. Why minus omega squared? Well, the S is equal to j omega. That means j omega times j omega. Since j times j is minus 1, you get this minus here in front of this omega squared. And this is just j omega, and then also times this expression in the brackets. You can also calculate here the absolute value, which is the magnitude, using this formula, which is familiar from complex analysis. Alright, it was our example considering the extra element theorem applied on this circuit where we see 3 resistors and 3 capacitors, which will be in this case a second order system. We have designated our extra element, in this case as C2, and worked out the steps in order to get this transfer function using this theorem. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.